Hello everyone, and welcome. Today, we're diving deep into critical, frequently encountered file systems powering Linux, powering macOS devices. While much evidence comes from Windows, overlooking X4, overlooking APFS can cost you crucial evidence. These OSs are pervasive in servers, cloud infrastructure, Internet of Things devices, and creative and development sectors. Understanding their structure isn't academic. It's a fundamental forensic skill to uncover data others miss and build defensible cases. In my experience in the field and in the classroom, confidently navigating non-Windows environments separates a good examiner from a great one. Imagine analyzing a compromised web server hosting illegal content. That server is likely running Linux using ext or ext4, or a corporate espionage case with a graphic designer's MacBook Pro. Her device runs macOS using Apple File System APFS. In both scenarios, one-size-fits-all forensics fails. You need specialized knowledge to correctly interpret timestamps, recover deleted files, and trace user activity. This is essential stuff. This session is designed to give you exactly that specialized knowledge. We will be building upon the foundational concepts from Module 7 of our course, but we are going to go much further than the textbook and slides. Our goal is to bring these file systems to life with practical, hands-on demonstrations and real-world examiner tips from years of casework. We will move beyond theory and into application, not just what an inode is, but how to use inode metadata to track a file's history. Not just talk about APFS snapshots, but how to use APFS snapshots as a goldmine for building timelines. This practical focus is designed to build your confidence and your competence. Think of today's session as a guided tour through two important and often misunderstood digital landscapes. We will start by exploring the logical and physical architecture of Linux's ext4, demystifying inodes and links. Then, we will journey into the world of macOS, tracing the evolution from HFS Plus to the modern APFS, and highlighting the features that most impact your forensic analysis. Finally, we will equip you with the open-source Linux forensics tools, showing you how to properly image a drive with DC3DD, and how to begin your analysis with both the sleuth kit and autopsy. By the end of our time together, you will be better prepared for your labs, better prepared for your certification exams, and ultimately, better prepared for your future career. To ensure we stay on track and make the most of our time, let's lay out a clear roadmap for what we aim to accomplish. First and foremost, we have 3 core learning outcomes for this session. By the end of our 55 minutes, you will be able to describe Linux file structures. We will focus on the components of ext4, the critical role of inodes, and the difference between hard and symbolic links. Second, you will be able to describe Macintosh file structures. We will cover the evolution from HFS Plus to APFS, the forensic implications of catalogs, B-trees, and snapshots. And third, you will be able to use core Linux forensics tools. We will cover DC3, DD for imaging, the sleuth kit, and autopsy suite for analysis. These outcomes are our guiding stars for today. Our session is structured into 3 main acts, followed by a quick review. The entire video is designed to run for about 24 minutes, keeping it concise and packed with valuable information. The first part of our session will take us to about the 18-minute mark, and is dedicated to Linux file structures. We will cover the history of the ext file system family. Then we will do a deep dive into the four main components of an ext4 volume. We'll spend significant time on inodes, the metadata powerhouses of Linux, and we'll clarify how the system uses links to manage file names and locations. This foundational knowledge is absolutely essential for any work you do on a Linux system. To truly understand how to forensically analyze a Linux system, we must first appreciate the history and evolution of its most common file system, the extended file system, or ext. This family of file systems has been the default for most Linux distributions for decades, and the journey begins with the second extended file system, or ext2. Introduced in 1993, ATX2 offered support for larger file sizes and longer file names. It was reliable and efficient for its time, but it was vulnerable to data corruption if the system crashed or lost power unexpectedly, because there was no mechanism to ensure pending write operations were completed. That vulnerability led to the development of the third extended file system, ext3, introduced in 2001. The key innovation of ext3 was journaling. A journal is a special log file on disk where the file system writes a description of changes before making them to the main part of the file system. If the system crashes, on restart the file system can read the journal, see any incomplete transactions, and either complete them or roll them back to bring the file system back to a consistent state. This dramatically reduced the time needed for file system checks after a crash and improved data integrity. For forensic examiners, this meant seeing fewer instances of unexplained file system corruption on ext3 systems. Then came ext4 in 2008, which is now the default for the vast majority of Linux systems you will encounter. ext4 adds many significant improvements while maintaining backward compatibility with ext2 and ext3. One of the biggest changes was the introduction of extents, replacing the traditional block mapping scheme. An extent is a contiguous range of physical blocks. Using extents reduces fragmentation and improves performance, especially for large files. ext4 also massively increased the maximum sizes for both individual files and the entire file system, pushing the theoretical limits into the exabyte range. From a forensic standpoint, ext4 brings several important changes. It supports nanosecond timestamp resolution, which can help in building tighter timelines of activity. It allows for longer file names, and it uses a more flexible block group structure that improves performance and scalability. Crucially, because an ext4 file system can be mounted as an ext3 file system, examiners must be careful to positively identify the true version they are dealing with. Understanding this evolution from ext2's basic structure to ext3's journaling to ext4's scale and efficiency is the first step to being able to properly dissect and analyze the evidence recovered from modern Linux machines. Now that we have a sense of its history, let's break down the fundamental architecture of an ext4 file system. At a high level, you can visualize an ext4 partition as being divided into four primary components. Think of these as the four pillars that hold up the entire structure. These are the boot block, the super block, the inode blocks, and the data blocks. Every single piece of information, from the operating system's bootloader to the contents of a user's text file, lives within one of these areas. As an examiner, understanding the role of each component is not just academic, It tells you where to look for specific types of evidence and how the file system organizes itself. The first component, the boot block, is a small reserved area at the very beginning of the partition. Its primary purpose is to contain the initial bootstrap loader code that the computer's firmware executes to begin loading the operating system. While often small and sometimes unused on non-bootable partitions, it is the absolute first point of call for a system starting up from that disk. For forensic investigators, the boot block can occasionally hold remnants of bootkit malware or non-standard loaders, making it a place you should not overlook, even though it is not part of the file system's data management itself. Following the boot block, we find the core organizational components. The partition is divided into a series of block groups, which are like mini file systems that help manage the disk space more efficiently. At the start of the first block group, and with backup copies in others, you will find the superblock and the group descriptors. The superblock is the master record for the entire file system, containing critical metadata like the total number of blocks, the block size, and the number of inodes. The inode blocks contain the inodes themselves, which are the data structures that store all the information about a file except for its name and its actual data. We will spend a lot of time on these soon. Finally, we have the largest area of the file system, the data blocks. This is where the actual content of your files is stored. Every photo, every document, every line of code, every executable program resides in one or more of these data blocks. The inode provides the map, and the data blocks hold the treasure. This separation of metadata in the inode from the content in the data blocks is a core design principle of Unix-like file systems. This elegant division is what allows for powerful features like hard links and is central to how we perform tasks like file recovery, as we will see shortly. To get a feel for this, let's look at some real commands. Shows us file listings with metadata. Notice the columns for permissions, owner, size, and the file name itself. The inode isn't directly visible here. To see the inode's contents, we use the command. Now we see it all: the inode number, link count, ownership, and those critical timestamps. Tools like can scan a device for physical errors, but be extremely careful with device-level commands. Now, let's see links in action. First, we create a simple file. We create a hard link using. This creates a new name pointing to the same inode. Then, a symbolic link using. This creates a new file that points to the path of the original. When we list the inodes with, notice that the original and the hard link share the exact same inode number, while the symbolic link has its own. This is the key takeaway. The inode tracks the number of hard links. The data is only truly gone when that count reaches 0. All right, we have just completed a deep dive into the structured and logical world of the Linux ext4 file system. Now, we pivot into a different, equally important ecosystem, Apple's Mac OS. For decades, Macs have been mainstays in creative industries, academia, and software development. As a forensic examiner, you will inevitably encounter a MacBook, iMac, or Mac Mini as evidence. The story begins with the original hierarchical file system, or HFS, introduced by Apple in 1985. In 1998, with Mac OS 8.1, Apple introduced HFS Plus, a major overhaul designed for the gigabyte-sized hard drives of the era. HFS Plus added journaling for reliability, support for longer Unicode file names, and Unix-style file permissions. The next great leap came in 2017 with macOS High Sierra and the introduction of the Apple File System APFS. APFS was engineered from the ground up, optimized for flash storage, and packed with features that have profound implications for digital forensics. One of the most unique features of HFS and HFS Plus is the concept of forks. A single file could have a data fork for user content and a resource fork for structured application data. When analyzing older Mac evidence, you must use tools that can parse both forks, as ignoring the resource fork could mean missing crucial metadata or embedded assets. HFS Plus divides a volume into logical blocks, typically 512 bytes, but allocates space to files in larger groups called allocation blocks. To improve performance, it often allocates space in clumps of contiguous blocks, which helps reduce file fragmentation. This leads to the concept of logical versus physical end of file. The unused area in the last block, known as slack space, can contain remnants of previously deleted files. Unlike ext4's distributed inodes, HFS Plus centralizes all file and folder metadata into a single, critical file called the catalog file. To search this massive file quickly, HFS Plus organizes it as a B-tree, a self-balancing structure that allows for incredibly fast lookups, insertions, and deletions. APFS revolutionizes this with its concept of a container. Multiple logical volumes can live inside one container, all flexibly sharing the same pool of free space. Its most significant architectural change is the copy-on-write metadata scheme. Instead of overwriting data in place, APFS writes changes to a new location, preserving the old data. This enables its most powerful forensic feature, snapshots. A snapshot is a read-only, point-in-time instance of the file system. For an examiner, this is an absolute goldmine. It allows you to travel back in time to view and recover files as they existed before they were deleted or modified. When investigating a Mac, focus on key artifacts like property list, files for settings, and SQLite databases, which apps like Safari and Mail use to store user history. Finally, remember that acquiring a modern Mac is complex. You must plan for file vault encryption, adjust secure boot settings in recovery mode, and manage disk arbitration to prevent altering evidence. In this final act, we will roll up our sleeves and explore the powerful open-source tools within the Linux ecosystem for performing digital forensics. We begin with the most critical step, evidence acquisition. The foundational principle is to preserve the original evidence by working on a forensically sound bit-for-bit copy. This requires a write blocker to prevent any modification of the source and a process of verification using cryptographic hashes. While the classic commands can copy data, the tool of choice for this task is developed by the DoD Cybercrime Center. DC3DD enhances with crucial forensic features like on-the-fly hashing, progress reporting, and detailed logging. But this power comes with a significant responsibility. The cardinal rule of imaging is to never, ever confuse your source drive and your target drive. Accidentally reversing your input and output will irreversibly destroy your original evidence. There is no undo button. To prevent this, always use a strict verification process. Positively identify your device names using a command like /all. Let's walk through a practical command. We specify our input file, our output file, the hashes to generate, and a log file to document the process. Once executed, begins the imaging process, providing real-time feedback. Upon completion, the log file contains a verifiable record of the entire acquisition, which becomes a critical part of your chain of custody. With our image created, we turn to analysis. The Kali Forensics menu gives us a tour of available tools, but our focus will be on the Sleuth Kit and Autopsy. The Sleuth Kit, or TSK, is a collection of command line tools for deep file system analysis. Autopsy provides a user-friendly graphical interface on top of that powerful engine. A typical TSK workflow starts with DC3DD to list the partition layout and find the offset of the volume we want to analyze. Next, we use DC3DD with that offset to get detailed statistics about the file system itself. Then, DC3DD lists all file and directory names, including entries for deleted files. If we find an interesting file, we can recover its content using DC3DD and its inode number. While the command line offers precision, Autopsy excels at visualization, allowing you to browse the file system, preview files, and automatically build a timeline of events. But what if the file system metadata is destroyed? This is when we turn to file carving. Tools like DC3DD ignore the file system and scan the raw data for file signatures, the headers and footers of known file types. It carves out this data and saves the recovered files, but they will lack their original names and timestamps. Carving is a powerful last resort technique, but all carved files must be manually reviewed and validated to ensure they are not corrupted. We have covered a tremendous amount of ground. We recapped our 3 pillars, the structures of ext4, the architecture of HFS Plus divided by APFS, and the workflow of core Linux forensic tools. To solidify this knowledge, let's finish with a quick quiz. Question 1. Name 2 ext4 advantages over ext3. The correct answers include the use of extents and support for much larger volumes. Question 2. What key info is stored in an inode? The file name and path. That information lives in the parent directory. Question 3. What is one difference between a hard and symbolic link? A hard link points to an inode, while a symbolic link points to a path. Question 4. Why are APFS snapshots helpful to examiners? They allow you to time travel to view and recover files as they existed in the past. And question 5. What mode is needed on Mac OS to adjust secure boot before imaging? You must boot into recovery mode. I hope this session has demystified these complex file systems and given you the confidence to tackle your labs and future cases. Remember to download the command list from the course page. And for deeper study, I highly recommend Brian Carrier's definitive text. Stay curious, be methodical, and never stop learning. The challenges are complex, but the work is rewarding. Thank you for your time. I look forward to the great work you'll do. Good luck, and I'll see you in the next module.